Bueno, pues buenos días a todos y bienvenidos nuevamente a esta tercera y última jornada del Congreso MATCOMP. Good morning to everybody and welcome again to this last day of the Congress, MATCOMP Congress. We are going to start today, this last day of the Congress, with another keynote presentation. So first of all, for me it is really a pleasure to present you today the next speaker we are going to have. So first of all, I would like to thank Mr. Andreas Erber from SLG Group for being here today. I know you've been having a quite tight agenda this week, so we really appreciate your effort for being here today, and at least to be here for the last day of the conference. In terms of the different keynote presentations we have been having during the Congress, we've been covering different topics and different perspectives. So we had a keynote presentation addressing more aeronautics with the perspective of a Tier 1 supplier. Then also yesterday we have a presentation more focused on automation by field. And then there was also a first keynote presentation more focused on wind energy sector. So I think today we will focus especially in automotive, which is of course a key topic which is attracting a lot of interest in the composite community. And at the same time, I think the presentation from this morning will be very interesting also because we will have the perspective of a raw material supplier. So SGL, you all know they are supplying different types of raw materials, and especially they are providing the carbon fiber, so which is of course a key raw material for high performance composites. So before we start, just a few words about our speaker, Andreas Erber, career. So right now, Andreas is the director of the Lightweight and Application Center at SLG Group that has been recently created, and with very, very interesting state-of-the-art equipment for different applications, development and demonstrations, as you will see. Andreas worked previously at SGL as head of thermoplastic composites in 2015, and also as a senior program manager at SGL also between 2011 and 2014. Andreas holds a PhD in aerospace engineering from the University of Stuttgart. So the title of the presentation for today will be Composite Intensive Lightweight Design in Automotive, Today and Tomorrow. So the estimated time for the presentation would be around 45 minutes, including maybe a few minutes for questions. So Andreas, please.
Thank you. So thank you very much for the introduction. Thank you very much for the opportunity to present what we are doing here as SGL in automotive. Arriving yesterday to the right time, so directly in front of the dinner, and then being back at the hotel, I was a little bit worrying that I will be the only one here tomorrow. So thank you very much that you showed up at 9. I will present one slide, only one slide about the company, and all the rest is focused on automotive. So SGL Group in the past worked, and also today, with the element carbon. But our roots are not carbon fibers, it is carbon electrodes. And these big electrodes you use for recycling, melting steel. So the electrode steel, therefore you use this electrode and consume it during the recycling. But due to the steel crisis, what has its kind of origin in China, we had there some problems, and we sold this business unit to a Japanese company, Shobadenko, and the remaining SGL group is presented here. We have two business units. One is a business unit for graphite materials and systems, so many of your cell phones, the lithium-ion battery, the anode material will be from us. A big electric-driven car out of the US has its electric battery system provided with our material. These are the things what GMS is doing. The business unit where I belong to, Composite Fibers and Materials, yes, we have a carbon fiber, but there is even more, and I will show you that, and I will show you that in relation to automotive. We invest nowadays. We want to grow 50% on the basis of 2015 turnover. In 5 years, 50% growth. So it's an interesting time, and in this time where you can shape things. For example, the Lightweight and Application Center. The agenda of the presentation, I try to be in time, 45 minutes. Motivation and state of the art. Where do we come from? Automotive, what do we do today in general, but also SGL Group. SGL Group addresses the biggest automotive composite programs what we have nowadays, and what will come next. So coming next, comprehensive material systems. What can we offer here? What can we do in terms of supply chain? What can we do in terms of process chains? So I will show you some ideas, innovative materials and process chains. And then last but not least, and this is something you already know, just to change a material, having a part and change nothing, only the material from metal change to composite. This will never ever be a success story. It will not be light, it will be heavy, and it will cost too much. So therefore, addressing upcoming automotive components means starting with a white sheet of paper and go for design and engineering, and then design and engineer. That's the key to enable automotive in the future, and I will show you our thoughts, what we have as SGL Group on that. Composites has a history coming from aerospace for sure. In automotive, you all know at Sunday, Formula One race cars, so everything done by hand. A rich race car team has 7 monocoques for each season. So that's their volume, what they have. They do it in pre-preg and autoclave. They do it by hand. This is not related to automotive. Formula One is not automotive. It's a great fun, but it's not the thing what we are looking for. Then we had the first small series, also as SGL addressed that. Audi, for example, the R8, Class A carbon, it looks very nice. You sell the look, therefore the price level is somewhere, but it's again not the thing what we all together want to discuss today in automotive. One major step was the i3 and i8. Here, an OEM started with a white sheet of paper, painting, drawing a carbon composite life cell. We build up together the infrastructure, the supply chain, and I will show you also that also BMW has made its lessons learned, because another product what is on the street nowadays, the 7 Series, addresses carbon totally different compared to this, what you can see here with the i3 and i8. So the carbon core technology of the 7 Series. And what will come next? Vision 2030. We will see that we will have a mixture of materials, high-strength steels, aluminum, and composites. Composites means glass fiber. At dedicated load passes, we will see carbon fibers. And if we are talking about carbon fibers, we are very sure if we want to go to real high volume, and that's more than i3, i8, or 7 Series, real high volume, that we will have many, many applications in thermoplastics. So thermoplastics reinforced by glass fiber, dedicated areas reinforced by carbon. What are requirements? I mean, first of all, if you want to go into composites, you should analyze your car, and this is one example Audi, for example, did this tool, developed this tool together with a university to look where are the load passes. I mean, if you have a component like a knot where you have very isotropic load passes, maybe die casting of aluminum is a good solution. Yeah? But if you have parts, components, where you have like the windshield, the B-pillar, where you have clear load passes, then it makes sense to use carbon fiber, because a carbon fiber with a clear direction can use its performance very well. But then again, it means do not make a quasi-isotropic laminate. Yeah? That is not the right approach. I know that we have it today, but we will see tomorrow in the future that we have also laminates which are really load pass oriented at these kind of components which I showed. But then there are still some open challenges. How do you join these materials? Multi-material design, you have to bring them together. Different thermal expansion, delta alpha topics, yeah? How to do that, how to cope with corrosion, how to integrate in existing assembly lines such components. Existing assembly lines in automotive means spot welding, and now we have here composites. E-painting, the KTL, is a challenge. So this challenge you can address all these by process chains, and that's a nice thing for us, by the materials. We have some materials, yes, we have fibers, we have also a carbon fiber, that's true, but we have also acrylic fibers. Why do we have acrylic fibers? We have acrylic fibers because we need acrylic fibers as a source for our precursor. So we produce our precursor by our own. We have also precursor supply by a joint venture together with Mitsubishi Rayon. So there are different sources. And the precursor, polyacryl nitrile, is an acrylic fiber. And therefore, we have in Portugal, next to Lisbon, we have a plant for acrylic fibers. And we have an acrylic fiber business. So going to clothes, going into roofs of convertibles, tennis balls, things like that. And the precursor for the carbon fiber. Yes, we have carbon fibers. We have oxidized fibers going into aerospace, for example, brake discs. We have some specialities like stretch broken yarns, chopped fibers, and many, many materials. You see the list of materials, starting from textiles, woven, non-wovens, non-crimped fabrics, but also impregnated textiles like prepregs, or in the thermoplastic world, organosheets and UD tapes. And we have this activity lightweight and application center, because we learned, and I will come to that later, that just putting a material on the table, having a price tag on it, and some mechanical data, nothing will change. It will happen nothing. You have to support your customer to bring the material via design, engineering, prototyping to an application. And if this application is good with respect to costs, lightweight, but also robust production, then you have a chance that this component will be in composites, and then companies like SGL have a chance to sell a material. We have a global presence, not very strong in Asia today. We have to change that. So it is very focused on Europe. So we have the precursor plant, so following now the process chain. We have the precursor plant in Lavradio, together with Mitsubishi Rayon precursor joint venture in Otake, Japan. We have 2 sites for the carbon fibers, one in Scotland at Murrayford. You don't know Murrayford, but you know Loch Ness, it's next to it. At Loch Ness there is the carbon fiber plant. Another one is in the US at the west coast, Washington State, Moses Lake. Then we have several material plants in Gardena, California, Philadelphia, and in Germany, north of Germany, south of Germany, Wackersdorf in Bavaria. And together, you know that maybe with Benteler, we have a joint venture, Benteler SGL, we're producing components together. So it is from the acrylic fiber downstream to the component and the assembly of modules, what we are covering as SGL Group. Comprehensive material systems. You will find this kind of puzzle 3 times because we are talking about toolboxes. And this is our textile toolbox. We have also a thermoplastic toolbox and a thermoset toolbox. Textile toolbox means we have textiles like woven materials, fabrics, non-crimp fabrics, but also smaller, thinner, not that width textiles to do local reinforcement, non-wovens to have a more isotropic behavior. And you can get these textiles with different sizings on the carbon fiber. A sizing which is friendly to epoxy, a standard sizing you already know. We have also sizing which are dedicated to thermoplastics, and in the thermoplastic arena we have also developed a sizing which works pretty good with in situ polymerization, so processing caprolactane, for example, you can do with these kind of materials. Thermoplastics, classical thermoplastics, I'm not talking now about the in situ polymerization. It's the same story. You have organosheets, bigger panels based on UD layers, based on woven layers, and you have unidirectional tapes to do local reinforcement. You can use these tapes for fiber placement to have limited scrap only. We have a material which can be used to produce ribs, so it has to flow. It is LFT, injection molding you can do, and then you can produce laminates reinforced by ribs, so you have strength and stiffness gained through the material, but also through the design, therefore these ribs. And you can combine all of these materials, therefore toolbox and this puzzle as kind of how we want to show it to you. And you can have it in carbon and in glass, and again that's important because we will see, I already said that in the future, that we will have composites, composite components, which have much glass fiber, and only there where it is needed we have the carbon fiber, and therefore you have to do it like this toolbox, you have to combine it, and that's possible with these materials. And if you are now wondering why someone from SGL is saying some limited carbon fiber is okay, but just imagine if we have at every car only 1 kilogram carbon fiber, the whole world is sold out. Carbon fiber has not that much capacity compared to steel and aluminum, that's clear. What are the advantages of the thermoplastics? Why we think that we will see it at highest volumes? You can combine the materials, what I already showed. You can address very easily recycling because you can remelt it and use it again. You can weld it, so this offers new process chains to build up the body in white. And what is also very nice, you can get out very, very fast from the much more cost-intensive tools, the press tools. So because you do not have to infuse the material, it's already there. You do not have to ship it cooled. So these are all advantages. And then you can have very low takt times at the pressing at the tier 1 or OEM. These are all advantages why we think that we will see thermoplastics at high volume production. Now going more into the material. I said we have a nice sizing working very well for thermoplastics. Here is an example for polyamide 6, nylon 6. What you can see here is the carbon fiber. It's a 50K carbon fiber, 50,000 filaments, with epoxy sizing, epoxy-friendly sizing, embedded into nylon 6. And I hope you can see it. After fracture, you see the carbon fibers are naked. There is no connection. And you can also see there are holes. So it is a performance which is okay, but it's not good. You can do it better. And now we have clever chemists within SGL. I do not understand chemists, but I can see what happens. They do different mixture formulations of the sizing. For sure, there are some particles of thermoplastic in the sizing. And then you see, after fracture, after the breakage of the specimen, there is material, matrix material, still at the fiber. There are no holes like here, and therefore it is a 90-degree bending what we have here, so fully stressed to the fiber matrix interface. And you see, if you just change the sizing, and carbon fiber supplier can do that, you can get out much, much, much more performance. We have this product on the market since 3.5 years, and selling these materials to customers doing organosheets and tapes. But we produce tapes and sheets also in-house. So we have UD tapes based on a 50K, a heavy toe. We have it at different widths. We can do that customized as well. So if you have a machine which needs a tape this or that width, we can do it. In that case, it was a nylon 6, 50K heavy toe. But if you want to go to a different kind of polymer, here we are flexible. This is important. We have no relationship to any polymer supplier. So customer defines, maybe it's a strategic definition, we can do that. Customized organosheets based on UD tapes, for example, different layups. But we have also slitted UD tapes to use them into in a weaving loom. So these are fully impregnated UD tapes woven. And with this kind of material, you combine toughness of a weave. Let's think about crash, energy absorption. You combine that with all the advantages what we discussed already of thermoplastics. So this could be a nice idea. And what we have here as well, nonwovens. These nonwovens are based on secondary carbon fibers. Secondary fibers means we produce fabrics at our plant in Wackersdorf. I will come to that later. Customers cut out their components of the fabrics, and there are cut-offs. And these cut-offs are recycled. Recycling sounds a little bit, it's not that nice. It's secondary carbon fiber, and we produce these non-woven materials. We combine it with polypropylene, for example, and then we have an organosheet based on secondary carbon fiber addressing the thermoplastic process chain. LFT material, I think that's clear for you. We can use that for injection molding. What is nice here, again, it is based on a heavy toe 50K fiber with a thermoplastic sizing at the surface. This is something what is unique. And then the toolbox that's missing, standard thermoset materials, the same philosophy, you already know it. We have pre-preg material with a certain width. We have a so-called taupreg. I will show that in details later. It is a yarn which is fully impregnated by a thermoset matrix, so the fiber volume content is already set. It is somehow cured. It's not tacky. It's dry. But it's still a textile, it's not a rod. Yeah? So you can use that for local reinforcement, you can use it for fiber placement technologies. We have these impregnated non-woven materials. These materials you can use to build out the ribs again, so geometrical stiffness, and we can supply, if it is interested, stacks and adhesive films. E420, it is not related to food. That's the code of the resin. What is it? It is a so-called snap cure resin. This is a resin system you can store at room temperature for 4 weeks. It has a nice TG of 140 degrees C, and it cures 30 seconds for a millimeter. So it is fast curing, and therefore it's a snap curing system. And you can get these taupregs, for example, again in carbon and glass fiber. Here we have it. You can, I think, download the presentation if you are interested in much more details. Here they are. Comprehensive material systems. What do we use already today? Let's talk about composites today. Composites in automotive means there are several big platforms. One is the Audi platform, Audi MSS modular sports car system. This means this is a platform where you have the R8 on, as well as the Lamborghini Huracan. And regarding our value chain, this is a nice story because we produce the carbon fiber, we produce the fabric, we produce the preforms, we do wet pressing, RTM and so on, so we produce the components, and we assemble the components to the module, the rear bench. And this rear bench module goes then to Audi or Italy for the final assembly line. And this is very good because if you master the entire value chain, you can learn a lot back and forth. To design a material like this means problems or advantages in the process chain here and there, and vice versa. What are the challenges of a wet pressing with respect to a fabric? Yeah, this we can steer very well if we have the entire value chain in hand. Another story, i3, i8. I do it a little bit quicker because I'm very sure you know that already. It is a car which is dedicated to carbon composites. The lifestyle started from scratch, a composite component, a composite body in white. We, together with BMW, built up the supply chain. So SGL is producing with Mitsubishi the precursor. The precursor is then shipped to the US. Moses Lake. Why Moses Lake? It is 100% green energy, and it is cheap energy. It is based on hydropower. And therefore, we selected Moses Lake. Side story, Moses Lake, you can read it in the newspapers. We have their installed capacity of 9,000 metric tons. This is the biggest carbon fiber plant on Earth. And these carbon fibers we shipped then, shipped means really with a ship and by train, to Wackersdorf in Bavaria, because it's a green story. And in Wackersdorf we produce the fabrics. We produce also there these non-wovens based on the cutoffs, the secondary fiber, you can remember, that we can do at Wackersdorf. Here we have the capacity of 6,000 tons. There is now a gap, 9,000, 6,000. The other material is used in direct processing, let's say braiding, for example. Braiding, 7 Series, the new product on the market of BMW, and you see this is not much related to the design of the i3 or i8. Here we have a pure multi-material design approach. So we have different materials next to each other, and we have also within one component multi-material. The braided side frame, it is overbraided onto a thermoplastic tube, overbraided textile, then RTM, epoxy resin, and then this composite part is assembled with a metal C shape, and therefore the side frame is a multi-material component combining metal and composites, and this is then integrated into a multi-material body in white. And there are also some other components, and it's a nice body in white because it addresses so many technologies. There is wet pressing, there is RTM, there is kind of SMC, there is pre-preg patching of a B-pillar, braiding, so this is very good, and I would say this reflects the state of the art today. Here you can see some close-ups. It's, as I already said, a hybrid design, and it is a real high-volume production. Higher volumes we can find within SGL Group at the leaf springs. A leaf spring, typically done in steel. Here we have it in composites. It is glass fiber, because it has to be glass fiber. A carbon fiber will be too stiff. That's clear for you, I think. Therefore, we have it in glass fiber. And again, we buy a glass fiber. We produce the textile. We produce the preforms. We produce the leaf spring. And then we can gain this lightweight potential at the Sprinter or the Volkswagen Crafter. It's a nice story. But even much more impressive is this one here, at the platform of Volvo, where you have also the XC90, we have installed a capacity and produce over 550,000 pieces a year, continuous fiber reinforced polymers. And therefore, the question, can you ramp up, can you scale composites? The answer is already there, and it's realized. We do it day by day in Austria together with our partner Bentel. Now the question, what do we need to address upcoming platforms in the future? We need innovative materials and process chains, and we need design and engineering capabilities. This is a project what I want to show you in the framework of the leading edge cluster MyCarbon, MAI, Munich, Augsburg, Ingolstadt. So you can see it's automotive and aerospace. We have different goals there. So we wanted to drastically reduce process costs and material costs. And this project is a public funded project, 50-50 share, industry money, public money, with an overall volume of 80 million euro. And one project is the MyRecar with several partners, BMW, Brötchen, SLG Group, and so on. And what have we done there? The classical process chain you see here. So you have a fabric, you cut this fabric, you shape the preform, you cut the preform, you bring it into an RTM mold, you inject resin, curing system, and then you have done a component. We developed the process chain. We have a toolbox. We have a kind of 3D printer. It's a fiber placement machine, and then we just have to mold it. Infusion is not anymore relevant because the toolbox already has the resin system inside. This machine, what we have since during the project, we used it at Brötchen, and since last week we own such a machine. We have it in Meitingen in our plant. 16 lanes you can run in parallel, 1/4 inch width material, and you can deposit it. And these 16 lanes, each lane you can steer by its own. You can stop and start. So therefore, you can imagine if you have cutouts, if you have complex shapes, there is almost no scrap. And this is a dramatic advantage compared to fabrics and RTM technology. So you have here a video how this machine is working. So you do your design at a computer. So it is CAD, FEM, and then via a CAD-CAM module, you transfer it to the machine, and then it is working like a TESA roller. Yeah? So it is a linear axis movement, and within the head there are these 16 lanes. Each lane you can steer by its own. You activate the pre-preg material, the toe preg. You activate it. You need heat to have some kind of tech, because, as I said, at room temperature it's tech-free. So you lay up the material, you bring it out, you have to cut it somehow, that's clear, and then you have to stamp and cure it. Within my Recar, a component, it's a BMW component, undercarriage cover, and it has a deposition time. Is it high, is it low? We can discuss, but at least it is what it is. But what is important, we have a scrap rate of only 1%. And now compare it, please, with a non-crimp fabric, and you cut this out, this kind of component. And therefore, I think it's clear what is the main advantage of this kind of process chain. Design and engineering. This was the slide, and I use it again and again, showing the motivation for lightweight and applications. And if a raw material supplier, and you said SGL, and that's true, is a raw material supplier, has only fibers and materials and do not understand what is happening there at the application and cannot support and cannot discuss with the customer the process chains and the ramp-up scenario and so on, you will have a problem. And therefore, there was in the past a gap, and we decided that we want to close this gap with the Lightweight and Application Center, and we started this activity beginning of last year. So January 2016, I was the first and only member of this Lightweight and Application Center, and today we are close to 30 people working in the center, comprising design engineers, finite element engineers, prototyping, process engineers, and so on, as well as testing. So what can we do there? We can, from a white sheet of paper, support with a concept. We can bring this concept to CAD and FEM, and we can build up a prototype and test it. And we can also do the full factory layout, virtual factory simulation, and analyze takt time, analyze material flows, and so on. Still, it is the idea that the customer will do that and buys the SGL material. So these are services along the value chain, and I think you are aware about this value chain, what we can support. If someone needs only one element of that, we do it. If someone needs the whole value chain, and very often we see that people have decided to do something in composite but have no idea how, then we do the whole value chain. So it starts with concept development. We know our material. We have, and I hope I could convince you, out of BMW, Audi project, the Volvo project, we know process know-how. We have understanding about high volume production, and the customer from time to time knows his requirements. Then we select a concept, we bring it to CAD, we do the laminate design, we do the process simulation, for example, draping simulation, what you can see here, curing, impregnation, and then we can dimension the material, so stacking sequence layup, thickness, so strength, stiffness, crash, NVH analysis. And then we can produce this prototype in the computer. We have all our production cells at the center as a digital mock-up there, and then we can produce it there. We can give the first hint what could be attack time, what could be therefore the investment you have to do if you have to invest in parallel lines, for example. And then we can produce, and you see it's the same cell. In that case, it's a wet pressing cell, what is shown at the image. We can produce the components. And this means we have, again, to address our three material portfolios, our three toolboxes: textile toolbox, thermoset, and thermoplastic. And this means also a lightweight and application center is a heavy invest, because if you invest now in RTM, tomorrow there will be a project in thermoplastics. If you go for wet pressing, you will see something in protrusion. So therefore you have to have all these technology in-house, and then you are prepared to discuss with the automotive customers. This means we have today 1,000 square meters, at Christmas 1,500 square meters, where we have equipment installed: pultrusion, robot-based filament winding, RTM, wet pressing, thermoforming. We have an autoclave as well, because we're also doing aerospace, cutters, and so on and so on. This machine, last week, we installed it, and injection molding machine will come within the next 4 weeks. I don't have it in mind directly, and some others until Christmas. Design and engineering, we have fully fledged all capabilities. We are using CATIA, we are using Abacus. If you want to go for LS Dyna, PEMCrash, and so on, we will go for these licenses. And one example, if you have all these in-house, if you have all these capabilities, and here we did it together with Fraunhofer because it's a big machine, is this front end, and it shows also again the toolbox approach, toolbox of thermoplastic, because we have here at this front end, we have the whole structure first of all produced in injection molding. The granulate was reinforced by glass fiber, so LFT glass fiber. You can see it here. We have a dedicated load passes, unidirectional carbon fiber-based tapes. We have, and I know that it is not symmetric. On the one side, we have tape woven sheets. At the other side, we have standard organo sheets, because it's a demonstrator and it wants to show that you can produce in a super short takt time, you can produce these kind of components comprising several materials based on thermoplastics. So to sum up, yes, carbon fiber reinforced polymers is still a small niche. Nevertheless, there are some pioneering activities done in the past, I3, I8. The lessons learned are done. New products based on the lessons learned are on the market. We saw and already see and still see a transfer from manual production to automated serial production. We cope with the challenges for multi-material design, and there are answers for these challenges. You need the right process chains, but you need also the right materials, and materials means a comprehensive material system. And what is also very, very important, and therefore, once again, thank you to having me here, you need the right partners. The low flip project we had together with Technalia, you need the right partners and the right network, because one company alone, no chance. We have to work together, and therefore, again, thank you very much to have me here in Spain at your conference this week. I thank you very much for your attention. Muchas gracias. Thank you.
Gives us a very good overview of composites in automation today, and some hints also for future.
Yeah.
So, some questions from the audience?
I already said the dinner, yeah?
Okay, I have one question myself. Well, you've been showing us many different materials and technologies, but you have mentioned quite a lot about thermoplastics.
Yeah.
And there you have mentioned maybe a couple of technologies. From one side, thermoplastic RTM, from another one, another side, organosheets.
Yep.
How do you see potential of these two technologies in the future?
Yeah. Thank you for the question. I mean, why have I had the highlight of thermoplastics? I mean, we saw in the past and we see today the thermoset technologies, but there will be and there is a certain limit in volume. So a 7 series you can do in RTM and wet pressing for sure, but think about you want to go for the famous Golf, for example, or we have many discussions with the Asian market. Let's assume what happens if there is a platform of Hyundai and you have to address that. And there we think we will have thermoplastics, therefore future thermoplastics. We think this will happen. That's the reason why I have it in the presentation. Now the two technologies. I think what you always have in technology, what we had also at wet pressing and RTM, there will be somehow two waves. The first, change to thermoplastics, yes, and there I think the first application will be based on organosheet and tape reinforcement. And then the technology will be ready for thermoplastic RTM, so in situ polymerization, and we are very sure this will be the future for the highest volumes in thermoplastics. The materials are there, the process chains are somehow there at tooling and automation. Maybe there are some challenges. If all these are done, we will see that in future. And sorry for the long answer. We saw it also at RTM and wet pressing. The i3 and i8 started with many parts in RTM, and then they learned, and now it's just the opposite. More parts are wet pressed than RTM. So there is a lessons learned within one technology, and we will see that in thermoplastic. It will start from our perspective in sheets and tapes, and then we will have the in situ polymerization, I think.
Thank you.
Thank you.
Any question from the audience?
Hello, morning.
Morning.
Thank you very much for your presentation. It has been really interesting. You had mentioned before some points to be carefully dealt related to the carbon fiber with the composites in the automotive industry. That's the thermal expansion and the joining with the different materials, parts, and so on. But what about the damage tolerance? Have you been involved on the damage tolerance assessment with the automotive industry?
I had, before my time at SGL, it was at the beginning of the BMW cars, I was in technology consulting. There was a project together with TÜV, so the authority for the cars, how to repair and how to cope with damage tolerance. And the first idea was composites. They are used in Formula One. They can absorb energy and super. But that's not the idea if you talk about repair and then damage tolerance. And then there were many ideas. We need to paint it, that you can see a color code, and then we give the driver a sheet of paper. If it is green, everything is good. If it's yellow, maybe there's a small damage, and you can forget that. Yeah? And therefore, we learned the best thing is, again, to address it by the design, and we see it today. So the hang-on parts are done in thermoplastic injection molding. They are very flexible, they are very damage tolerant, and you can repair, means you have to replace them very easy. And the inner structure, the body in white, this is in thermoset continuous fibers. You can repair it, but there, if you have really crashed the cylinder, maybe we have to judge the overall car from an economic point of view. But my answer would be to address it by the design and not by much more robust materials, color codes, sensors, and things like that. Design. Thank you. I'm here anyway, so we can discuss later. Thank you.